In this webinar, I will show a bunch of techniques, methods and tricks for measuring signals and testing hardware with nothing more than an Arduino UNO board. So my name is Clemens Wellens, if you like. I work for Elektor and I will be presenting this webinar. This shows that for many measuring jobs, you don't need expensive equipment. Talking about expensive equipment, in this webinar we give away an expensive tool. Well, it's not that expensive, but it's still worth 250 euros. To win, or to make a chance to win this, you will have to fill in a form, and the URL will be posted in the chat box on the right bottom corner of your screen. And there will also be a code word that you must enter in the form, and the code word I will give it to you during this presentation. So here we go.
Okay, so why use a microcontroller? Today's test and measurement tools are almost always built around a microcontroller. Special circuitry adapts the signals to measure into something a microcontroller can handle. The microcontroller processes the data and prints the result as a numerical value on a display, or it shows the value in some other way, for instance as sound or light or a bar graph. In electronics, probably everything you want to measure can be converted into a voltage or a current, unless you have a very special needs. There are sensors for almost everything. Microcontrollers with built-in analog to digital converters can measure voltages. A current can be converted into a voltage, and therefore microcontrollers can also measure currents. If converting a quantity into a voltage or current is not possible, then there is time and closely related frequency. Many things can be converted into a frequency or a time interval. Currents and voltages too can be converted into a frequency, and so almost everything can be measured as time. Microcontrollers are great at measuring time. They have special timers and counters for that. Some quantities are easier to measure indirectly than directly. Measuring power, for instance, is easy when you measure both voltage and current and then do the necessary calculations to obtain the power. Microcontrollers can have many inputs, and so they can measure more than one signal at once. This is perfect for doing indirect measurements with multiple signals. Then there are situations where a current or a voltage or a frequency is needed to activate, excite or bias a circuit to measure something else, for instance an impedance. The digital outputs of microcontrollers are perfect for switching things on and off. They can also be used to produce short pulses to record, for instance, the impulse response of a circuit. Some microcontrollers possess a digital to analog converter, which can be used to generate excitation signals. If they don't have a digital to analog converter, then they can generate a time-based signal like PWM instead, as these signals can be turned into voltages and currents. These can then be used to power or bias a circuit or a component. Using its timers, a microcontroller can generate clock signals or square waves that can be turned into sine waves with a suitable filter. Sine waves are excellent for measuring and testing audio circuits. Microcontrollers are great at generating time-based signals. Finally, more and more sensors appear with built-in analog to digital converters. They output numerical values directly, usually on some serial communication bus like I2C or SPI. Microcontrollers excel at serial communications, and so they can communicate directly with digital sensors. So as you will have understood by now, microcontrollers are perfect devices to do measurements with, as they can measure almost anything, and this explains why they are found in almost every measurement instrument. The Arduino UNO board is basically a microcontroller breakout board for the ATmega 328 from Microchip, and so it can be used in test and measurement applications. It has up to 20 digital inputs and outputs and up to 6 analog inputs. It doesn't have analog outputs, but it can generate PWM signals on 6 pins. It has serial interfaces like I2C and SPI, and it has 3 timer counters. It features a serial over USB port that connects to a computer, allowing the Arduino UNO to send and receive data and to be remotely controlled. However, before we move on to Arduino, let's briefly discuss the goal of a measurement so that we can delimit our field of application somewhat. Several goals can be defined. To identify a signal, check the presence of a signal, check a signal's quality, or to compare signals. There may be more, but this is what I came up with. In the first case, you have no clue what to expect, and you just put an instrument on a wire to see if something is there, and if so, what. This can be risky for two reasons. First, you may damage the instrument if the signal is too far out of bounds for it. And second, you may misinterpret the results. Oscilloscope-like high impedance fast voltage monitoring or logging is probably your best bet, and this is a job microcontrollers usually can do pretty well. Also, as they are cheap, it doesn't hurt too much if your microcontroller breaks. Checking the presence of a signal might very well be the most common case. In this case, you know what kind of signal to expect, and all you want to know is if it is there or not. For instance, when debugging a user interface, you know that when the user presses a button, a certain signal should appear in the circuit. You know which kind of measurements to take, and precision and accuracy are not really important. This kind of measurement can be addressed with quick and dirty microcontroller programming. Checking a signal's quality, on the other hand, requires care, as it involves precision and accuracy. Now you must know what you are doing, you must know how a measurement can influence a signal. Microcontrollers can be used, of course, but both the input stage and the program must be designed carefully. It depends on the type of signal, of course, but it may be quicker to use a commercial instrument than to cobble up your own. Comparing signals can be done with a more or less crude microcontroller approach, as long as the signal features you are trying to compare are within the capabilities of the controller, and the approach, of course. If the signals to compare are acquired in the same way, then their quality will be similar, and so they can be compared. So, summarizing, if we don't consider digital serial bus sensors, we can use a microcontroller to measure voltages, time and frequencies. And as long as we are not looking for super precise results, we can do this with quick and dirty programming and interfacing. The Arduino UNO is perfect for the job. It is cheap and easy to get and specializes in quick and dirty programming. Its ATmega 328 microcontroller is an amazingly powerful device, yet easy to program, and this is made even easier by the Arduino programming environment and libraries. There are more than 4,000 registered libraries covering almost any sensor on the market. The Arduino UNO has 6 analog inputs, and signals in the range from 0 to 5 volts can be connected directly to the extension headers. Signals outside this range will need some sort of amplification or attenuation circuit that can be mounted on, for instance, a breadboard. The UNO has 6 semi-analog PWM outputs and in total up to 20 digital inputs and outputs. Of course, Arduino also supports several types of serial buses, so digital sensors can be used too. Reading signals that can only take on the values 0 and 5 volts, binary TTL level signals, so to speak, is super easy with the Arduino function digital read. You must first configure a microcontroller pin as an input and then you can read its value as high or low. If you do this in a loop, you can follow the evolution of a signal. Now digital read only reads one pin. If you want to read more than one pin, you can call digital read for each pin, but then the signals are not read at the same time and they will be out of phase. To avoid this, you must connect all the signals to pins of the same port, B or D, and read the pin B or pin D register. This way you can create a simple 8-channel logic analyzer. Of course, the loop must be fast enough to obtain meaningful results. With the Arduino function pulse in, you can measure the duration of TTL level active high or low pulses, ranging from 10 microseconds up to 3 minutes. The inconvenience is, however, that it blocks, meaning that the program will wait until pulse in is done. Because pulse in has 10 microsecond resolution, it can be used to capture rectangular waveforms and serial communication lines, as long as they do not exceed, say, 40 kHz or so, to have a little bit of headroom. When you do this, it is probably a good idea to store the measured values in the microcontroller's memory before sending them all at once to a display or a computer. If you want to do other things during a pulse, you can measure it manually by using timestamps. For this, the Arduino function micros is practical. The program can monitor a pin for a level change, call micros to create a timestamp, wait again for a level change, but now in the opposite direction, and call micros again for a timestamp. The resolution is much lower, but you can read or write other pins during the pulse, for instance measure one or more voltages or blink an LED. This technique also works with analog inputs, allowing you, for instance, to measure the time a signal remains below a certain level. For even more control and precision, you can use the MCU's timers instead. They have event capture capabilities and can generate interrupts. But you must be careful which timer you use, as the Arduino libraries also use some of them. The Arduino UNO has 6 analog inputs that will work without configuring them first. You don't have to do this because Arduino does it for you. You can read the analog inputs with the Arduino function analog read. This will return a 10-bit value from 0 to 1023, which covers the input range from 0 volts up to the ADC's reference voltage minus 1 bit. By default, the reference voltage is 5 volts for the Arduino UNO, but it can be set to 1.1 volts with the function analog reference. It can also be set to use the voltage on the AREF pin. So, by default for the Arduino UNO, the function analog read has a resolution of roughly 5 millivolts and a maximum value of 4.995 volts. Note that the Arduino UNO is not recommended for high precision applications, as its analog input stage is not designed for it. Its ATmega328 microcontroller can do much better, but the printed circuit board of the UNO does not respect high precision analog design techniques. However, for basic voltage measurements it is fine. Another thing to be aware of is that analog inputs 4 and 5 may be a bit noisier than the others, as they are powered from the digital supply VCC and not from the filtered analog supply AVCC. Also note that the function analog read is slow, as the ADC clock is set to 125 kHz and the conversion consumes 13 cycles. This means that the conversion takes a bit more than 100 microseconds, which limits the sample rate to about 9 kHz. Therefore, the maximum frequency that can be measured without using advanced sampling techniques is about 4.5 kHz. Use a good low-pass filter for best results. Also, analog read blocks, and so calling it may significantly reduce the Arduino loop speed. By using the Arduino serial plotter built into the IDE, you can quickly make a simple oscilloscope. It is not really suitable for doing time measurements, but it allows you to visualize signals, analog as well as digital. Unlike digital inputs, it is not possible to read all the analog inputs at the same time. Therefore, signals will be out of phase unless you timestamp the samples, with the Arduino function micros for example, and correct them for time differences. If you have recorded samples, timestamped or not, then a better way to visualize them is by sending them to a computer to process them in a spreadsheet. A good way to do this is by sending the samples over the serial port using the human-readable CSV format, comma-separated values. It doesn't have to be a comma, often a tab or a semicolon is fine too. Most spreadsheets can import CSV files directly, saving you the hassle of writing Python scripts to convert binary values into something usable. In general, I highly recommend transmitting, whenever possible, human-readable data over a serial port, as it makes debugging so much easier. Unfortunately, the Arduino serial monitor doesn't allow you to log or save data to a file, but you can copy-paste into Notepad or something similar. However, it's much easier to use a real serial terminal program instead, like Teraterm or RealTerm, and save to a file directly. Once the data is in the spreadsheet, you can analyze it in any way the spreadsheet allows you to, spectrum analysis for instance, and you can create pretty graphs. Before we move on to generating test signals with Arduino, first a quick word on input circuitry. Digital inputs can have a pull-up resistor activated. This is not a real resistor and its value depends on the input voltage, so unless you really need it, make sure to disable it. When a pull-up is activated on an analog input, it will influence the result. Digital inputs without pull-ups are high impedance and they are protected with over and under voltage diodes. This is nice, but not sufficient, and I therefore highly recommend using a series resistor, if possible, to limit the current that can flow into a pin. This will avoid damage if an input is accidentally configured as an output. The ADC inputs are optimized for signal sources with an output impedance of approximately 10 kΩ or less. They are not high impedance inputs as found on oscilloscopes and multimeters. It may therefore be necessary to insert a buffer between the signal of interest and the ADC input to avoid influencing or even destroying the input signal. As already briefly mentioned, analog inputs may need an anti-aliasing filter to improve the results, especially when signal frequencies get close to half the sample rate, which is about 4.5 kHz. You can use the Arduino function digital write in a loop to generate square waves or more complex signals, or very slow signals on one or more pins. To get a stable frequency, the loop must be timed by using, for instance, the function millis, and any interrupts that are running should be processed as quickly as possible. Like digital read, digital write can only do one pin at a time. To output more than one signal at the same time, use the port X register instead, like port B or port D. The MCU has timers that can be used to generate clock and PWM signals with very precise timings. With a bit of trickery, the MCU on the Arduino UNO can output square waves up to 8 MHz. Not every frequency from 0 to 8 MHz is possible, but timer 1 has a resolution of 16 bits and several prescalers. Timer 0 and 2 are both 8-bit. Timer 0 is also used for the millis and delay functions, so be careful what you do with it. The Arduino function tone is an easy way to generate a square wave on any GPIO pin of the microcontroller. You can optionally specify a duration in milliseconds, so burst signals are easily created. However, the minimum frequency is 31 Hz, while the maximum frequency is limited to 65,535 Hz. So other techniques must be used to generate square waves with frequencies outside this range. Also keep in mind that tone can only use one pin at a time, so it's not possible to do multiple tones simultaneously. It is also possible to misuse the serial port or the SPI port for generating frequencies and complex waveforms. As an example, sending the hexadecimal value 55 on a serial line with one stop bit and no parity will result in a square wave with a frequency that is equal to the baud rate divided by 2. The Arduino UNO cannot produce real analog signals, even though the Arduino function analog write lets you believe otherwise. Instead, this function controls the duty cycle of a fixed frequency PWM signal on one of 6 predefined outputs, 3, 5, 6, 9, 10 and 11. The idea is to turn the PWM signal into an analog voltage by adding a low-pass filter to it. In most cases, a simple RC filter is enough. The PWM signal's frequency on pins 3, 9, 10 and 11 is rather low, only 490 Hz. It is 980 Hz on pins 5 and 6. Faster PWM is possible, of course, but then you must configure a timer yourself. Arduino uses timer 0 for PWM on pins 5 and 6, and this timer is also used for the millis and delay functions, so be careful with it. PWM pins 9 and 10 use timer 1, which has 16-bit resolution. PWM outputs 3 and 11 both use timer 2. Because the PWM frequencies are rather low, out-of-the-box analog write is not suitable for generating test signals like 1 kHz sine waves or so. It can be done though if you increase the frequency of the PWM signals. Outputs 9 and 10 are the most suitable for this as they use timer 1, which is not used by anything else. If you set timer 1's prescaler to 1, the PWM frequency will go up to 62.5 kHz, which allows the generation of much faster analog signals. Now you can do, for instance, frequency sweeps up to 20 kHz to determine the transfer function of an audio filter or amplifier. Note that for higher frequencies you should use a lookup table and a phase accumulator instead of calculating waveforms on the fly. I will not go into that here. Finally, sometimes a random or noise signal is needed for testing or measuring something. Such a signal too can be generated with an Arduino UNO by using the function random that produces pseudo-random numbers. They are not 100% random, as the sequence repeats itself after a very long time, but for most applications they are good enough. You can use the random numbers directly with analog write to control a PWM signal, for instance, or extract a single bit from them to use with digital write. Okay, that's it. I've shown you how many test and measurement tasks can be done with a cheap Arduino UNO board and a little bit of programming. Not every possibility has been explored. The Arduino API features more functions that can be useful in your application. Also, you don't have to stick to the Arduino API and libraries. The full power of C and C++ is at your disposal. You can, of course, improve and extend the presented material to create elaborate instruments, but that was not the goal here. Our goal was to do things without too much effort. I hope you can apply it to your applications and experiments as well. There's now time for questions. You can type them in the chat box below.
My next Elektor webinar will be about charging batteries with solar energy, and this is scheduled for September 28, which is in about 6 or 7 weeks. That would be at 4 o'clock, 1600 hours Central CEST. Okay, so I hope to see you then again. In the meantime, goodbye.